What if everything we thought we knew about gravity, the force that holds planets in orbit, keeps us grounded on Earth, and shapes the very fabric of the universe, was just part of the story? Picture this: galaxies spinning faster than they should, spacecraft drifting off course in ways no equation can predict, and cosmic structures behaving as if invisible hands are tugging at them from the shadows. These aren't just glitches in our calculations, they're cosmic puzzles that have physicists questioning whether gravity alone can explain the universe we see. For centuries, from Newton's apple to Einstein's warped spacetime, gravity has been the undisputed ruler of the cosmos. But what if it's time to rewrite the rules? Think about the last time you looked up at the night sky. Those distant stars and swirling galaxies seem to move in perfect harmony, obeying the laws of gravity as we understand them. But dig deeper and the picture gets stranger. Take galaxy rotation curves, for example. Stars at the edges of galaxies orbit so fast that, by our current laws, they should have been flung into the void long ago. Yet there they are, defying expectations. Or consider the Pioneer anomaly, where spacecraft billions of miles from Earth experienced tiny, unexplained accelerations, like something out there was gently pulling them off course. These aren't small discrepancies, they're glaring signs that our cosmic blueprint might be missing a few pages. So what's really going on? Some scientists point to dark matter, an invisible substance that could make up most of the universe's mass. Others propose radical ideas like modified gravity, where the force itself behaves differently on cosmic scales. And then there are those who dare to ask, could there be entirely new physics at play, forces we haven't even dreamed of yet? This isn't just about filling in gaps, it's about reimagining the universe from the ground up. Over the next few minutes, we'll dive into these bold theories, meeting the minds who challenge gravity's reign and exploring what their ideas could mean for the future of physics. Buckle up, because the cosmos is about to get a lot more mysterious. Einstein's theory of general relativity is one of the most brilliant achievements in human history, a masterpiece that reshaped our understanding of space, time, and gravity. But even this towering framework has its limits. Take the way galaxies spin, for instance. According to relativity, stars on the outer edges of galaxies should move slower than those near the center, just like planets farther from the sun orbit more sluggishly. Yet when astronomers measured these rotations, they found something startling. Stars at the edges whip around just as fast as those closer in. It's as if the galaxy is held together by an invisible glue, something our equations don't account for. This mismatch is so glaring that scientists had to invent an entirely new concept to explain it: dark matter, a mysterious substance that doesn't emit light or interact with ordinary matter, yet somehow makes up most of the universe's mass. But the surprises don't stop there. In the late 1990s, astronomers made another jaw-dropping discovery. The universe isn't just expanding, it's accelerating outward faster and faster. This flew in the face of everything we knew. Gravity should be pulling the cosmos back together, slowing the expansion, not speeding it up. Once again, scientists scrambled for an answer, landing on another enigmatic fix: dark energy, a repulsive force that counteracts gravity on cosmic scales. Together, dark matter and dark energy make up 95% of the universe, leaving the ordinary matter we see, stars, planets, galaxies, as just a tiny fraction of reality. It's a humbling thought. The very forces we thought governed the cosmos might be mere footnotes in a much larger story. And then there's the elephant in the room: quantum mechanics. While relativity reigns supreme in the vastness of space, the subatomic world dances to an entirely different tune. Particles pop in and out of existence, entangled particles communicate instantly across vast distances, and gravity, the force that shapes galaxies, becomes utterly negligible. The two theories, relativity and quantum mechanics, are like two languages describing the same universe, but they refuse to translate smoothly. Efforts to unify them, like string theory or loop quantum gravity, remain tantalizing but unproven. This rift suggests something profound. Gravity, as we know it, might not be the final word. So where does that leave us? If our best theories can't explain the universe without inventing invisible entities, maybe it's time to rethink gravity itself. What if, instead of searching for hidden forces, we've been missing something fundamental about the one we thought we understood? That's where alternative theories step in, frameworks that rewrite the rules entirely. From modified gravity to higher dimensions, these ideas don't just patch the holes in our knowledge, they invite us to see the cosmos in a whole new light. Imagine holding a map of the universe where everything you can see, stars, galaxies, swirling nebulae, amounts to less than 5% of what's actually out there. The rest, an invisible scaffold called dark matter, a cosmic ghost that refuses to interact with light, yet bends the very fabric of space with its gravity. This isn't science fiction, it's the leading explanation for why galaxies don't fly apart, and why the universe behaves in ways our equations can't explain. Think of it like this: if the cosmos were a stage play, visible matter would be the actors under the spotlight, while dark matter is the hidden rigging holding the entire set together. The evidence for dark matter is written across the sky. Take galaxy clusters, for instance, colossal families of hundreds of galaxies bound by gravity. When astronomers measured their mass using the light from stars and gas, the numbers didn't add up. There simply wasn't enough visible matter to account for the gravitational glue keeping these clusters intact. Then came the clincher, gravitational lensing, where the gravity of these clusters bends light from distant objects like a cosmic magnifying glass. The distortion was far too strong for visible matter alone, implying something massive and invisible was doing the heavy lifting. Yet here's the twist: despite decades of hunting, no one has ever directly detected dark matter. Underground labs shielded from cosmic noise, sensitive detectors buried deep in mines, even experiments on the International Space Station, all have come up empty. This absence has fueled skepticism. Could dark matter be a placeholder, a mathematical band-aid for a deeper flaw in our understanding of gravity? Enter modified gravity theories like MOND, modified Newtonian Dynamics, which suggest that gravity behaves differently at cosmic scales, eliminating the need for invisible matter altogether. In this view, dark matter isn't a substance but a signpost pointing to physics we've yet to grasp. The debate rages on. Proponents of dark matter argue that the sheer weight of indirect evidence, from galaxy rotations to the cosmic microwave background, can't be ignored. Skeptics counter that inventing an undetectable substance to save our theories feels like painting the universe by numbers. What if dark matter is a cosmic mirage, a shadow cast by something even stranger? As we peel back the layers of this mystery, one thing becomes clear: whether it's an unseen particle or a rewrite of gravity's rules, the universe is far weirder and more wonderful than we ever imagined. What if the answer to the cosmic mystery of galaxy rotation wasn't an invisible substance but a simple tweak to the laws of gravity itself? That's the radical proposition behind modified Newtonian dynamics, or MOND, a theory that dares to rewrite Newton's centuries-old equations to explain the universe without dark matter. At its core, MOND suggests that gravity doesn't fade as quickly over vast distances as we once thought. Instead, at the outer edges of galaxies, where stars defy expectations by orbiting just as fast as those near the center, gravity might play by different rules. It's like discovering that the familiar pull holding you to the ground subtly shifts when you're far from home, a small change with cosmic consequences. The beauty of MOND lies in its simplicity. While dark matter requires inventing an entirely new form of matter, MOND adjusts the math we already have. Take those puzzling flat rotation curves of galaxies. In Newton's original framework, stars on the outskirts should slow down like a spinning ice skater stretching their arms. But under MOND tweaked equations, their speed holds steady, no invisible glue needed. Even more striking, MOND accurately predicts the motions of dwarf galaxies, tiny cosmic islands where dark matter models often stumble. It's as if the universe left us a subtle clue. Maybe the force we thought we knew has been hiding secrets all along, yet MOND isn't without its critics. When faced with the titanic gravity of galaxy clusters where the pull is so strong it bends light into arcs, the theory strains to keep up. These cosmic heavyweights seem to demand the extra heft of dark matter, leaving MOND to patch gaps with adjustments that some call contrived. And then there's the elephant in the room, Einstein's relativity. MOND was born from Newton's playbook, and merging it with the warp and weave of spacetime has proven messy. Without a relativistic version that fits seamlessly into our broader understanding, MOND risks feeling like a temporary fix, a brilliant hack, but not a complete solution. The debate between MOND supporters and dark matter advocates is anything but academic. It's a clash of philosophies. Do we chase unseen particles or rethink the laws themselves? Proponents of dark matter point to the mountain of indirect evidence, from the cosmic microwave background to the large-scale structure of the universe. MOND enthusiasts counter that science should prize elegance. Why invent dark matter if a subtle gravity tweak does the job? The tension between these views isn't just healthy, it's essential. Every great leap in physics has come from questioning the unquestionable, and MOND, whether ultimately right or wrong, forces us to do just that. But what if both paths are just the beginning? Beyond MOND and dark matter lie even wilder ideas, theories that imagine gravity spilling into hidden dimensions or emerging from the quantum chaos of spacetime itself. If history teaches us anything, it's that the universe rarely fits neatly into our boxes. Whether MOND is a stepping stone or a detour, one thing's certain: the final answer, when it comes, will rewrite more than just our textbooks. It'll redefine how we see the cosmos. What if gravity isn't a fundamental force at all but an illusion, a cosmic mirage conjured up by something far stranger happening beneath the surface of reality? That's the mind-bending proposition of emergent gravity, a theory pioneered by physicist Eric Verland. Imagine the universe as a vast, tangled web of quantum information, where every particle, every star, every galaxy is connected by invisible threads of entanglement. In this view, gravity isn't a force that pulls objects together. It's more like the tension on a stretched rubber sheet, emerging from the way information itself is woven into the fabric of spacetime. Think of it like temperature. We feel heat and cold every day, but zoom in, and temperature disappears. It's just the frantic dance of atoms. Emergent gravity suggests something similar. What we perceive as gravity might be the statistical outcome of countless quantum interactions, a shadow cast by deeper, invisible processes. This idea builds on the holographic principle, which claims our three-dimensional universe could be a projection of information encoded on a two-dimensional surface, like a cosmic DVD encoding an entire movie. If that's true, gravity isn't the star of the show, it's just a special effect. Verland's theory takes this even further. By treating spacetime as a kind of quantum network, his equations naturally reproduce the effects we usually attribute to dark matter and dark energy, without needing to invent mysterious substances. Picture a galaxy's rotation curve again. Instead of invoking invisible matter, emergent gravity suggests the extra pull comes from the way entropy, the universe's tendency toward disorder, reshapes spacetime itself. It's as if the cosmos has a hidden tax code, and gravity is the bill we've been misreading for centuries. But not everyone's convinced. Critics point out that emergent gravity's math remains incomplete, struggling to explain phenomena like black holes or the precise details of galaxy clusters. And without experimental proof, it's hard to say whether this is a revolutionary breakthrough or a beautiful dead end. Yet the theory's elegance is undeniable. It dares to ask whether we've been searching for ghosts when the real answer lies in rewriting the rules of the game. So where does that leave us? If gravity emerges from quantum entanglement, it would mean our universe is far more interconnected than we ever imagined. Particles separated by light years could still be linked, their hidden bonds shaping the very forces we thought we understood. This isn't just about fixing equations, it's about seeing reality as a vast, dynamic puzzle where gravity is just one piece. And if that piece isn't what we thought, what else might be hiding in plain sight? The answer could lie in the next frontier, quantum gravity, where the fabric of spacetime itself might unravel into something even more extraordinary. At the heart of modern physics lies an unsettling contradiction. Quantum mechanics and gravity refuse to speak the same language. On one hand, you have the quantum world, where particles flicker in and out of existence, defying certainty and dancing to the tune of probabilities. On the other, gravity sculpts the cosmos with smooth, predictable curves, bending spacetime like a silent artist. But when these two titans meet, say, at the crushing heart of a black hole or the fiery birth of the universe, the equations explode into nonsense. Singularities, those infinitely dense points where gravity's rules break down, taunt physicists with their paradoxes. How can something be both infinitely small and unimaginably massive? The uncertainty principle, which governs quantum realms, insists that spacetime should be frothy and chaotic at microscopic scales, a seething quantum foam. Yet gravity's equations demand a smooth, continuous stage. This isn't just a technical hiccup, it's a rift in reality itself. Enter loop quantum gravity and string theory, two ambitious frameworks trying to stitch this rift together. Loop quantum gravity imagines spacetime not as a smooth fabric, but as a tapestry of tiny, indivisible threads. Think of it as the pixels of the universe. These loops intertwine to create the illusion of continuity, much like a digital image blends countless dots into a seamless picture. String theory goes even further, proposing that all particles, including the hypothetical graviton, gravity's quantum messenger, are vibrations of infinitesimal strings humming through higher dimensions. Both theories are mathematically elegant, offering glimpses of a unified cosmos. But here's the catch: neither has produced a shred of experimental evidence. After decades of work, we're still waiting for a testable prediction that could confirm whether these ideas describe reality or just beautiful fiction. The graviton exemplifies this tension. If gravity is indeed a fundamental force, it should have a quantum carrier like the photon does for electromagnetism. Yet gravitons remain stubbornly hypothetical, their existence inferred only through mathematical necessity. Some models suggest they're so weak they'd rarely interact with matter, explaining why we've never detected one. Others argue that if gravitons exist, they might leak into hidden dimensions, evading our instruments entirely. But what if the search for gravitons is a red herring? What if gravity isn't a force to be quantized at all, but something else entirely? This is where the plot thickens. Even loop quantum gravity and string theory, for all their creativity, assume gravity is fundamental. a force to be unified, not explained away. But emergent gravity and other radical ideas flip the script, suggesting that spacetime and its curves might arise from deeper quantum interactions. Picture a whirlpool in a river. The water's motion creates the illusion of a persistent structure, but the whirlpool isn't a thing itself. It's a pattern emerging from countless molecules in motion. Could gravity be the same, a side effect of quantum entanglement or thermodynamic shuffling? The implications are staggering. If gravity isn't fundamental, our hunt for gravitons or a theory of everything might be missing the forest for the trees. Perhaps the answer lies not in forcing quantum mechanics and gravity into marriage, but in realizing they're describing different facets of a truth we haven't yet grasped. From black holes to the Big Bang, every cosmic mystery we've touched might be pointing us toward a reality far stranger, one where gravity isn't the architect of the universe, but a shadow cast by something deeper. And if that's true, the greatest discoveries in physics are still waiting, hidden in the quantum whispers of spacetime itself. Picture our universe as a thin slice of reality, a three-dimensional membrane, or brain, floating in a higher dimensional space like a leaf on the surface of a vast, unseen pond. This is the heart of brainworld theory, a radical idea that suggests gravity might be the only force capable of leaking beyond our brain into the extra dimensions surrounding us. Why does gravity feel so weak compared to electromagnetism or the nuclear forces? In this view, it's not feeble, it's just diluted, its strength spread across dimensions we can't perceive. Like a voice echoing down a long hallway, most of gravity's signal fades into the unseen, leaving only a faint whisper in our familiar three-dimensional world. This elegant twist could solve two cosmic puzzles at once. First, it offers a fresh take on dark energy, the mysterious force accelerating the universe's expansion. If gravity spills into higher dimensions, its grip on our brain would naturally weaken over time, mimicking the repulsive effect we attribute to dark energy. Second, it explains why gravity is exponentially weaker than other forces. While electromagnetism and nuclear interactions are confined to our brain like ink trapped on paper, gravity's influence bleeds outward, thinning its presence in our reality. The Randall-Sundrum model, one of the most promising brainworld frameworks, takes this further. It proposes that our universe sits near a higher dimensional bulk, warped in a way that amplifies gravity's effects at small scales while masking them across cosmic distances. This could have startling consequences like microscopic black holes, fleeting and tiny, that might form in particle colliders or cosmic rays. These would vanish almost instantly, evaporating into the bulk, but their brief existence could leave detectable traces. So far, no such signals have been found, but the search continues. Yet for all its ingenuity, brainworld theory remains unproven. Extra dimensions, if they exist, are either curled up impossibly small or just beyond our perceptual reach. Some argue this makes the idea untestable, a clever mathematical story with no anchor in reality. Others counter that absence of evidence isn't evidence of absence. After all, neutrinos were theorized decades before they were detected. The universe has a habit of hiding its most profound secrets in plain sight. If brainworlds feel like science fiction, consider scalar tensor theories, another bold reimagining of gravity where its strength isn't constant but varies across space and time. Here, gravity could be influenced by hidden scalar fields, invisible partners that tweak its behavior in ways that mimic dark matter or dark energy. Like brainworlds, these theories blur the line between force and geometry, suggesting that what we call gravity might be just one expression of a deeper, more dynamic reality. Whether through hidden dimensions or evolving fields, the message is clear. the cosmos refuses to be confined by the rules we've written for it. What if gravity isn't just a fixed law of nature, but a force that changes its strength over time, shaped by hidden influences we've yet to fully uncover? That's the provocative idea behind scalar tensor theories, where gravity isn't a solo act but partners with an invisible scalar field, a kind of cosmic dial that tweaks its power across space and time. The Brans-Dicke theory, one of the earliest and most influential models, proposed this exact scenario. Instead of Einstein's static gravitational constant, imagine gravity's intensity shifting subtly, like a dimmer switch on the universe's lights. This isn't just a mathematical curiosity, it could explain some of cosmology's biggest puzzles, from the explosive growth of the early universe to the eerie acceleration of its expansion today. Take inflation, the brief but colossal stretching of spacetime moments after the Big Bang. Standard models rely on a hypothetical inflated field to drive this rapid expansion. But what if inflation wasn't a separate mechanism at all? In scalar tensor frameworks, gravity's fluctuating strength could have powered inflation naturally, with the scalar field acting as the universe's throttle. Fast forward billions of years, and that same variability might account for dark energy, the mysterious force pushing galaxies apart. If gravity weakens over cosmic distances or epochs, the effect would mimic an anti-gravitational push, eliminating the need for dark energy as a distinct entity. It's a tantalizing two-for-one, one dynamic force explaining two of the universe's greatest enigmas. Yet this flexibility comes at a cost. General relativity's elegance lies in its constant, unchanging numbers that anchor the equations. Introduce a variable gravitational constant, and suddenly, the universe's rulebook feels less like a timeless manifesto and more like a draft with scribbled revisions. Critics argue this undermines the predictability that makes physics so powerful. After all, if gravity's strength can drift, how do we trust any measurement across cosmic history? Supporters counter that nature isn't obligated to conform to our love of simplicity. The universe might well be a patchwork of adjustable parameters, with gravity's fickleness not as a flaw but as a feature waiting to be decoded. This debate echoes an older idea, Mach's principle, which suggests that inertia, the resistance of objects to changes in motion, isn't an intrinsic property but emerges from the gravitational influence of all matter in the universe. Einstein toyed with this concept while crafting general relativity, but it never quite fit. Now, scalar tensor theories are reviving the discussion. If gravity's strength is tied to a scalar field influenced by the cosmos's total mass and energy, Mach's intuition might find new life. The distant stars and galaxies could be subtly shaping the force you feel when you trip on the sidewalk, linking every motion to the grand tapestry of the universe. Whether scalar tensor theories ultimately hold up or not, they remind us of a profound truth. The laws we take as gospel might be more fluid than we imagine. From Brans-Dicke's pioneering work to today's cutting-edge models, the quest to understand gravity keeps revealing layers we never anticipated. And if history is any guide, the next breakthrough won't come from polishing old equations, but from daring to ask whether the force we thought we knew has been hiding in plain sight all along. Ernst Mach once asked a deceptively simple question: why does a spinning bucket of water climb up its sides? The answer, he argued, wasn't just about the bucket, it was about the stars. Mach believed inertia, that stubborn resistance to motion we all experience, wasn't a property of objects themselves but a cosmic conversation, a backreaction from all the matter in the universe. Picture this: when you push a book across a table, the resistance you feel might not come from the book alone but from the gravitational whispers of every galaxy, every star, every speck of dust in the cosmos. It's as if the universe itself is saying, "This is how things move here." Einstein was so captivated by this idea that he called it Mach's principle, weaving threads of it into general relativity. But the math never quite fit until now. Modern physicists are giving Mach's principle a quantum makeover. In these updated models, gravity isn't just a one-way street where matter bends spacetime. Instead, spacetime's structure and even the strength of gravity itself could be shaped by the universe's total energy and mass. Think of it like a cosmic feedback loop. The distribution of matter defines gravity, and gravity in turn dictates how matter moves. Some theories take this further, suggesting that what we call local gravity might just be a holographic projection, a shadow cast by interactions at the universe's boundaries. It's a radical shift. Gravity isn't a force imposed on the cosmos, but an emergent property, a collective agreement between every particle in existence. This isn't just philosophical musing, it has real consequences. If Mach was right, even tiny changes in the universe's large-scale structure could tweak gravity's rules in measurable ways. Imagine a galaxy moving differently because distant clusters shifted, or a lab experiment detecting subtle inertial effects tied to the cosmos's expansion. Some researchers are already exploring whether dark energy, the mysterious force accelerating the universe, could be a Machian side effect, a cosmic recalibration of inertia as the universe grows emptier. Others tie it to quantum entanglement, where particles separated by light years remain mysteriously linked, their hidden connections subtly shaping the fabric of spacetime itself. But here's the twist. If gravity is cosmic peer pressure, what happens when the crowd disagrees? Enter Torsion, a forgotten player in gravity's game. While Einstein's relativity treats spacetime as a smooth, twistable fabric, Einstein-Cartan theory adds a new wrinkle: tiny, subatomic spirals in spacetime itself, like microscopic corkscrews woven into the cosmic canvas. These twists could explain why particles have spin, why black holes behave oddly, and even how Mach's principle might operate at quantum scales. It's a reminder that gravity, whether emergent or fundamental, is far from a settled story, and the next chapter might be written in geometries we've only begun to imagine. Einstein's general relativity paints spacetime as a smooth, curving fabric, but what if that fabric isn't just bending? What if it's also twisting, like a cosmic spiral staircase hidden in the geometry of the universe? That's the wild idea behind Einstein-Cartan gravity, a theory that adds a new ingredient to the mix: torsion. Unlike relativity, where matter warps spacetime through curvature alone, here, spinning objects, from electrons to black holes, leave their own unique imprint, twisting the very structure of reality around them. Imagine rolling a bowling ball across a trampoline. In Einstein's world, it creates a dip. But in Einstein-Cartan's universe, if the ball were spinning, it'd also tug the trampoline's fabric into a corkscrew. This subtle twist could solve some of gravity's biggest headaches. Take singularities, those infinitely dense points at the center of black holes where physics breaks down. In Einstein-Cartan gravity, torsion prevents spacetime from collapsing into a true singularity. Instead, the spin of collapsing matter creates a repulsive effect, like a cosmic spring that bounces back before reaching infinite density. The result, a black hole's heart, might not be a mathematical nightmare, but a dense, turbulent region where spacetime churns like a whirlpool. Even more intriguing, torsion could explain dark matter without invoking invisible particles. The collective spin of galaxies might weave a network of twisted spacetime, creating extra gravitational pull where none seems to exist, like a hidden hand guiding stars from the shadows. Recent simulations lend weight to this idea. When researchers modeled galaxies using torsion-based equations, the results eerily matched real-world observations: flat rotation curves, gravitational lensing, even the motions of dwarf galaxies, all without a speck of dark matter. It's as if the universe handed us a puzzle and we've been missing half the pieces, but there's a catch. Einstein-Cartan's math is notoriously complex, a labyrinth of tensors and spin connections that make even seasoned physicists reach for aspirin. For many, the elegance of curvature-only relativity is hard to abandon for a theory that demands such computational gymnastics, yet the allure of torsion refuses to fade. If spacetime really does twist, it could rewrite not just gravity but particle physics too. Protons, electrons, and quarks all carry intrinsic spin. What if that spin isn't just a property but an active participant in shaping the cosmos? This isn't just about fixing equations. It's about seeing the universe as a dynamic, interwoven tapestry where matter and geometry dance together. And if torsion seems mind-bending, wait until you hear its cousin, teleparallel gravity, where spacetime isn't curved or twisted but built from a lattice of distant cosmic threads, each tugging the others into place. The stage is set for a revolution, one where gravity's secrets might lie not in the fabric of spacetime, but in how it's stitched together. Suppose everything we thought about gravity, Einstein's warped spacetime, the cosmic trampoline bending under mass, was just one way of seeing the picture. What if curvature isn't the main event but a sideshow? That's the bold claim of teleparallel gravity, a theory that tosses out curved spacetime entirely and replaces it with something far stranger, a cosmic web of twisting, interconnected threads. In this view, gravity isn't about the dips and valleys of spacetime, but about the angles between distant points, like a vast invisible scaffolding holding the universe together. The math is breathtakingly elegant instead of wrestling with curvature's complexity. Teleparallel gravity describes gravity through torsion alone, a geometric twist that somehow replicates all of general relativity's triumphs without bending an inch. Take the motion of planets, for instance. Einstein's equations predict their orbits by treating spacetime as a flexible sheet deformed by the sun's mass. Teleparallel gravity gets the same results but through a completely different mechanism, the alignment of distant reference frames, as if the solar system were a finely tuned clockwork where each gear's spin influences the others across empty space. Even black holes, those ultimate tests of gravity's might, emerge not as singularities but as dense knots in this cosmic net, their immense pull explained by the way the web tightens around them. It's a radical shift in perspective, one that doesn't just mirror general relativity but strips it down to its essence, suggesting curvature might have been a detour all along. Where teleparallel gravity truly shines, though, is in its flirtation with quantum theory. While general relativity's smooth spacetime clashes violently with quantum mechanics' chaotic granularity, teleparallelism's threaded universe offers a natural meeting point. Those twisting connections between points, they behave like a network of quantum links, echoing the entanglement that binds particles across vast distances. Some theorists argue this could be the missing bridge between gravity and the quantum world, a framework where spacetime itself emerges from something deeper, more discrete. Imagine if gravity weren't a force at all but a collective effect, like the way individual ants create the illusion of a single, intelligent swarm. Yet for all its promise, teleparallel gravity has skeptics. Detractors call it a mathematical sleight of hand, a clever reformulation of Einstein's ideas that doesn't actually predict new phenomena. After all, if it perfectly replicates general relativity's results, how do we test whether it's more than just repackaged genius? Supporters counter that the real value lies in its potential to simplify the path to quantum gravity. By replacing curvature with torsion, teleparallelism might untangle the knotted math that's blocked progress for decades. And then there's the tantalizing hint that on the tiniest scales, Planck lengths, where quantum foam froths teleparallel gravity's woven structure might finally diverge from relativity, offering experimental footholds future probes could grasp. The debate forces a profound question. Is spacetime's curvature fundamental or just a convenient illusion? If teleparallel gravity is right, we've been staring at the shadow on the cave wall, mistaking it for the object itself. But to find out, we'll need more than equations. We'll need to look for gravity's fingerprints in places Einstein never imagined. Which brings us to an even wilder possibility. What if gravity isn't just twisted or curved, but fundamentally non-local? Its influence weaving through the cosmos in ways that defy our intuition about space and time. Newton's original vision of gravity was simple, a force acting instantly across the void, tugging the moon toward Earth and planets toward the sun with no delay. Einstein rewrote that script, replacing Newton's mysterious action at a distance with the elegant curvature of spacetime, a cosmic dance where gravity's influence travels at the speed of light. But what if the truth lies somewhere in between? Enter non-local gravity, a radical revival of Newton's idea, now dressed in the language of quantum mechanics and cosmic memory. Here, gravity's effects aren't confined to the here and now. They ripple across spacetime in ways that defy conventional cause and effect, as if the universe itself refuses to forget. At the heart of this idea is a quantum twist, entanglement on a cosmic scale. Just as particles can become mysteriously linked, their fates intertwined no matter how far apart. Non-local gravity suggests that spacetime itself might carry hidden connections, threads of influence that bypass the usual speed limits. Picture a black hole's crushing grip. In Einstein's framework, its gravity warps nearby space, but in non-local models, its pull could echo backward and forward in time, like a stone's ripple in a pond affecting waves that haven't even formed yet. This could explain some of cosmology's thorniest puzzles. Take dark energy's relentless push. Instead of an unknown force, it might be gravity's delayed reaction to the universe's explosive birth, a kind of cosmic recoil from the Big Bang's aftermath. Recent studies have given this wild idea surprising traction. Papers in journals like Physical Review show how non-local equations can match the observed acceleration of the universe without invoking dark energy. The math suggests that gravity might remember past configurations, its strength modulated by the history of spacetime itself. It's as if every galaxy, every star, leaves a gravitational fingerprint that lingers, subtly shaping the future. Even black hole singularities, those infinitely dense points where relativity breaks down, might vanish in this framework, smoothed out by the universe's refusal to let any event exist in isolation. Yet for all its theoretical appeal, non-local gravity faces a glaring hurdle. How do you test it? If gravity's influence can leap across time and space, untethered from strict locality, experiments become fiendishly hard to design. Detecting these effects would require measuring deviations so subtle they're drowned out by cosmic noise, like listening for a whisper in a hurricane. Some propose hunting for anomalies in gravitational waves, those ripples in spacetime first detected in 2015. If gravity truly has a memory, these waves might carry faint echoes of ancient cosmic events, imprints of a past that refuses to fade. Others suggest scrutinizing the cosmic microwave background for patterns that only non-local gravity could explain. This isn't just about rewriting equations, it's about reimagining causality itself. If gravity can reach across epochs, then the universe isn't just a collection of isolated moments, but a tapestry where every thread tugs on every other, no matter how distant. It's a vision that blurs the line between past, present, and future, hinting at a cosmos far more interconnected than we ever dreamed. And if non-locality seems mind-bending, just wait, because the next twist in gravity's story involves a universe where even light speed isn't sacred. What if the speed of light, the universe's ultimate speed limit, the unchanging constant at the heart of Einstein's relativity, wasn't so constant after all? That's the explosive idea behind Joe Megiddo's variable speed of light theory, a daring challenge to one of physics' most sacred tenets. Imagine a young cosmos where light raced across the newborn universe far faster than it does today, its speed gradually slowing as spacetime cooled and settled. This single tweak could rewrite cosmic history, offering an elegant solution to puzzles that have haunted cosmologists for decades. Take the horizon problem. Why does the universe look so uniform in every direction, as if distant regions once shared a secret handshake? Inflation theory says spacetime ballooned faster than light could keep up, smoothing everything out in a flash. But Megiddo's VSL suggests a simpler answer in the early universe. Light moved so quickly that distant corners could communicate, synchronizing their properties before the cosmic brakes kicked in. The flatness problem, another headache for cosmologists, might also crumble under VSL's gaze. Our universe's geometry is suspiciously perfect, balanced on a knife's edge between open and closed, with almost no curvature. Inflation stretches this fine-tuning into inevitability, but VSL achieves the same feat through light's fading sprint. As photons slowed, they carried away the energy that might have warped spacetime, leaving behind the eerily flat cosmos we observe. Even dark energy's mysterious push could be an illusion, a side effect of light's deceleration, warping our measurements of cosmic expansion. It's a breathtaking trade. Swap one fixed constant for a dynamic one, and suddenly, the universe's quirks snap into focus. But VSL doesn't just tweak equations, it appends them. Einstein's relativity hinges on light's speed as an immutable anchor, the glue holding spacetime's symmetry together. If that speed varies, the foundation cracks. Energy conservation, causality, even the predictable ticking of atomic clocks could unravel. Critics pounce on these violations, arguing that VSL trades one set of mysteries for another. Yet Megiddo and his allies counter that constants might be placeholders for deeper truths. After all, the gravitational constant isn't truly constant in many alternative gravity theories. Why should light's speed be sacrosanct? The boldest implication, though, isn't about light at all, it's about gravity's role in cosmic evolution. If VSL is right, then light's fading speed, not gravity's pull, might have sculpted the universe's large-scale structure. Galaxies, clusters, even the cosmic web could owe their forms to photons losing their cosmic marathon over eons. This flips the script entirely. Gravity, long seen as the universe's architect, becomes a secondary player, its influence dwarfed by light's primal sprint. Yet for all its audacity, VSL remains a fringe idea, a beautiful hypothesis lacking smoking gun evidence. No experiment has yet caught light red-handed, changing its speed over time. But the theory's value might lie less in its truth than in its defiance. By questioning relativity's untouchable constant, VSL reminds us that even the firmest pillars of physics are provisional, waiting for the next revolution to knock them sideways. And if light's speed isn't sacred, what else might be up for grabs? Perhaps gravity itself isn't a force, but something far stranger, a shadow cast by the universe's relentless drive toward disorder. That's where entropic gravity enters, turning thermodynamics into the new rulebook for the cosmos. Imagine the universe not as a grand stage governed by gravity's ironclad rules, but as a vast, churning heat engine, where the force we call gravity is just the universe's way of seeking equilibrium, like steam rushing to fill a vacuum. This is the radical premise of entropic gravity, Eric Verland's bold reimagining of gravity as an emergent property of thermodynamics, not a fundamental force. Picture a glass of water with a drop of ink diffusing through it. No invisible hand pulls the ink molecules apart. They spread simply because nature prefers disorder. Now apply that to the cosmos. What if gravity is just spacetime's way of maximizing entropy, its relentless drive toward chaos? Black holes offer the most tantalizing clues. When matter vanishes beyond an event horizon, it carries information with it, or so we once thought. But Stephen Hawking showed black holes emit radiation, slowly evaporating over eons. This revelation tied black holes to thermodynamics, giving them temperature and entropy. Verland took this further, suggesting that if black holes obey thermodynamic laws, maybe all gravity does. In this view, the force holding planets in orbit isn't a pull but a statistical tendency, a cosmic osmosis where matter rearranges itself to balance entropy gradients. It's as if the universe is a giant puzzle, and gravity is just the pieces sliding into the emptiest spaces. Dark matter's elusive nature fits eerily well into this framework. Instead of invoking mysterious particles, entropic gravity proposes that the extra tug we attribute to dark matter is really spacetime's hidden microstructure adjusting to entropy. Galaxy rotation curves, gravitational lensing, even the motions of galaxy clusters all could be side effects of this thermodynamic dance. Think of it like a crowd at a concert. You don't need to see every person to predict how the group will move. The collective push and pull emerges from simple rules. Entropic gravity treats the cosmos the same way, with gravity as the emergent rhythm of microscopic quantum shuffles. Yet for all its elegance, entropic gravity remains a work in progress. The theory lacks a complete quantum framework, leaving gaps in how exactly entropy gradients translate to the precise strength of gravity we observe. Critics argue it's more metaphor than mechanism, a beautiful analogy that hasn't yet hardened into testable math, but its conceptual power is undeniable. By reframing gravity as a thermodynamic phenomenon, Verland invites us to see the universe not as a machine governed by forces, but as a dynamic, evolving system where every galaxy, every atom, is part of a vast computation toward equilibrium. This raises a staggering question. Could the universe itself be a cosmic heat engine, converting energy into structure and back again? If so, gravity isn't the architect of order, but the byproduct of chaos, a shadow cast by the universe's tireless march toward disorder. And if that's true, the next leap in understanding might come from an even stranger idea, that all this complexity, from spinning galaxies to colliding black holes, is just a holographic projection of information encoded on the universe's outer edge. What if our three-dimensional universe, with its swirling galaxies and warped spacetime, is nothing more than a shadow, a holographic projection of information encoded on a distant two-dimensional surface? This is the heart of the holographic principle, a mind-bending idea that suggests gravity, matter, even reality itself might emerge from a cosmic code written on the universe's outermost boundary. Think of it like a movie. What we experience as the rich, three-dimensional world around us could be the playback of data stored on a flat, two-dimensional disk. The implications are staggering. Black holes, those ultimate destroyers of information, might hold the key. When matter falls into a black hole, its information isn't lost, it's smeared across the event horizon like ink on a celestial parchment, preserved forever in swirling quantum graffiti. The mathematics behind this is rooted in something called AD/CFT duality, a theoretical bridge connecting gravity in our three-dimensional world to a quantum field theory living on its two-dimensional boundary. In simpler terms, it's like having a magical dictionary that translates the chaotic dance of particles in a flat, quantum world into the curved, gravitational cosmos we inhabit. This duality doesn't just solve the black hole information paradox, it suggests that gravity itself might be an illusion, a side effect of quantum entanglement between bits of information on the edge of reality. Even dark energy, the mysterious force accelerating the universe's expansion, could be a glitch in the cosmic projection, a boundary effect rippling inward like a glimmer on a movie screen. But here's the catch: as elegant as the math is, we have no direct proof that the holographic principle describes our actual universe. The equations work beautifully in hypothetical, simplified models, like a universe with negative curvature, but applying them to the real cosmos is like trying to fit a square peg into a round hole. Some physicists argue this makes the idea untestable, a beautiful abstraction with no anchor in observation. Others counter that absence of evidence isn't evidence of absence after all. Black holes were once pure theory too. Which raises an even wilder question. If the universe is a hologram, could it be a simulation? Not in the sci-fi sense of alien supercomputers, but as a natural consequence of reality being fundamentally informational. The pixels of this cosmic display wouldn't be on a screen but woven into the fabric of spacetime itself, a self-sustaining code that generates gravity, matter, and even consciousness as emergent properties. It's a dizzying thought, one that blurs the line between physics and philosophy, and if holography seems abstract, wait until you hear its fractal cousin. Imagine gravity isn't just a projection but operates on multiple scales, repeating its patterns like a cosmic Russian nesting doll. From the whirl of galaxies to the spin of electrons, the same gravitational rules might apply, twisted and scaled but fundamentally unchanged. This isn't just about rewriting physics, it's about seeing the universe as a living, breathing fractal, where every layer reveals new depths of the same mysterious design. Imagine zooming into a snowflake. No matter how close you get, the same intricate patterns repeat, spiraling into infinity. Now picture the universe working the same way, with gravity's rules echoing across scales from the quantum foam to galactic superclusters. This is the wild promise of fractal gravity, where spacetime isn't smooth or neatly dimensional but a shimmering mosaic of repeating geometric patterns. At the quantum level, spacetime might resemble a chaotic foam, bubbling with fractal fluctuations. Zoom out to galaxies, and those same patterns could explain why stars at the edges orbit too fast. No dark matter required, just gravity operating differently when viewed through a fractal lens. The math behind this is as beautiful as it is bizarre. Ordinary physics assumes 3 spatial dimensions, but fractal models allow for fractional dimensions, say 2.7 or 3.3, where spacetime's structure crinkles like crumpled paper. These wrinkles could tweak gravity's strength depending on scale, mimicking dark matter's pull without inventing new particles. Think of it like walking through a forest. On the ground, trees block your path, but from a plane, the canopy looks smooth. Fractal gravity suggests we've been measuring the universe from the wrong vantage point, mistaking its textured geometry for missing mass. Yet for all its elegance, fractal gravity faces tough questions. How exactly do these fractal layers emerge from the soup of quantum mechanics? Why would nature prefer a universe that repeats like a cosmic hall of mirrors? And most crucially, where's the experimental proof? So far, the theory leans heavily on mathematical elegance, offering few testable predictions. Supporters argue that galaxy rotation curves align eerily well with certain fractal models, but skeptics counter that the same data fits dark matter just as neatly. Without a clear mechanism to explain how spacetime chooses its fractal dimensions, the idea remains a tantalizing sketch rather than a finished blueprint. That's where biometric gravity steps in, offering a different kind of layered universe, Instead of fractal dimensions, it proposes two separate metrics, two rulebooks for spacetime operating simultaneously. One governs the realm of stars and galaxies, the other dominates the quantum world, and where they overlap, gravity behaves in unexpected ways. It's like having two maps of the same city, each highlighting different landmarks. Only by combining them do you see the full picture. Could this duality, rather than infinite fractal layers, hold the key to unifying cosmic and quantum gravity? The answer might lie in the quiet hum of gravitational waves, where subtle anomalies could betray the presence of spacetime's hidden twin. What if the universe we see with its galaxies, stars, and planets is just one layer of reality, coexisting with a hidden twin made of something entirely different? That's the startling idea behind bimetric gravity, where spacetime isn't governed by a single set of rules but two parallel geometries, each with its own rhythm and structure. Picture a cosmic dance where ordinary matter moves to the familiar beat of Einstein's relativity, while an invisible partner, dark matter and energy, follows steps written in a separate gravitational language. This isn't science fiction. It's a serious attempt to solve two of cosmology's biggest mysteries by suggesting they're two sides of the same coin, bound together by gravity's shadow. The math behind this is as elegant as it is complex. In bimetric models, the universe has two distinct metrics. Think of them as separate rulebooks for measuring distance and time. One metric shapes the spacetime we know, dictating how light travels and planets orbit. The other, a shadowy counterpart, interacts with the dark sector, influencing the invisible scaffolding that holds galaxies together. The two metrics aren't entirely independent. They communicate through gravity, subtly tweaking each other's behavior. This interaction could explain why dark matter clumps around galaxies like an invisible halo, not because it's made of exotic particles, but because it's responding to a gravitational echo from this hidden twin. When tested against real-world observations, bimetric gravity delivers some surprising wins. It reproduces the flat rotation curves of galaxies, those head-scratching speeds of stars on the outskirts without requiring dark matter. It can even mimic dark energy's cosmic push, framing the universe's accelerating expansion as a side effect of the two metrics slowly drifting apart. It's as if the universe has been playing a trick on us all along, disguising the quirks of a dual spacetime as missing mass and energy. Yet for all its promise, bimetric gravity comes with hefty baggage. The equations are fiendishly difficult to solve, and while the theory can mimic observations, it struggles to make unique predictions that would set it apart from dark matter models. Worse, the shadow metric's influence is so subtle that detecting it directly might be impossible with current technology. Some critics argue this makes the theory untestable, a beautiful mathematical construct with no anchor in reality. Others counter that absence of evidence isn't evidence of absence. After all, gravitational waves were theorized a century before we detected them. The most tantalizing question remains: if a hidden spacetime exists, how deep does the rabbit hole go? Could there be more than two metrics, a whole family of spacetimes stacked like layers in a cosmic onion? This line of thinking leads straight to massive gravity, an even bolder idea where gravity itself has mass, warping the rules of relativity in ways that might finally bridge the gap between the quantum and cosmic realms. The journey to understand gravity's true nature is far from over, but with each twist, the universe reveals just how little we truly know. For centuries, physicists assumed gravity was carried by massless particles called gravitons, ghostly messengers flitting through the cosmos at light speed. But what if gravitons aren't weightless at all? Enter massive gravity, a theory that dares to give gravity itself a tiny mass. This isn't just a tweak, it's a seismic shift in how we understand the universe's most familiar force. If gravitons have even a whisper of mass, the implications are staggering. Cosmic acceleration, that mysterious push we blame on dark energy, might not need an exotic explanation. It could simply be gravity's newfound heft subtly altering its reach over vast distances. The math behind massive gravity is both elegant and treacherous. Unlike massless gravitons, which obey Einstein's relativity with pristine symmetry, massive gravitons introduce a subtle drag, like runners slowed by invisible sand. This drag could explain why gravity weakens faster on cosmic scales than our equations predict, mimicking dark energy's repulsive effect without inventing a new force. Picture a magnet losing its pull as you step back. Now imagine gravity doing the same, its influence fading just slightly faster across the universe's expanse. Suddenly, the accelerating cosmos isn't a puzzle, it's a natural consequence of gravitons finally admitting they have weight. Yet massive gravity's path is littered with pitfalls. Early versions of the theory predicted ghost modes, phantom particles with negative energy that would unravel spacetime's fabric. For decades, this seemed like a death blow. But breakthroughs in the 21st century, like the de Rham-Gabadad's Tolle framework, tamed these ghosts by carefully sculpting the equations. The result? A self-consistent theory where massive gravitons don't spell cosmic doom. It's a delicate balancing act, like building a skyscraper on quicksand possible, but only if every beam and bolt is perfectly placed. Here's the tantalizing twist. If gravitons have mass, it might finally explain why gravity is so laughably weak compared to other forces. Electromagnetism can hurl a fridge magnet against Earth's entire gravity with ease. But if gravitons are massive, their range could be inherently limited, like a radio signal fading into static. This wouldn't just solve hierarchy problems, it would rewrite gravity's role in the quantum realm, offering fresh clues to unite it with the other fundamental forces. Which brings us to supersymmetry, gravity's most elegant dance partner. If massive gravity is real supersymmetry, the idea that every particle has a hidden twin could provide the perfect stage. Supersymmetric particles might stabilize massive gravitons, weaving them seamlessly into the quantum tapestry. Or perhaps gravity's mass is a shadow of extra dimensions, where gravitons are bulkier because they ripple through unseen realms. The possibilities are as dizzying as they are profound. One thing's certain, if gravity has mass, the universe just got a lot heavier and a lot more interesting. Supersymmetry, or SUSY for short, is one of the most elegant ideas in modern physics, a cosmic mirror that reflects every known particle with a hidden, heavier twin. At first glance, it might seem like an abstract mathematical flourish, but dig deeper, and SUSY could be gravity's long-lost partner, the missing piece that finally bridges the quantum and cosmic realms. Here's how: every particle we know, electrons, quarks, photons, would have a superpartner with slightly different properties. The electron's twin, the selectron, would carry the same charge but be a force-carrying particle. The photon's counterpart, the photino, would have mass. This symmetry doesn't just tidy up the particle zoo. It could solve gravity's biggest headache, its glaring absence from the quantum world. The magic lies in the numbers. In our current model, quantum corrections should make gravity's strength balloon to unimaginable levels, yet it remains absurdly weak. SUSY particles cancel out these runaway calculations like cosmic accountants, balancing the books so gravity stays featherlight. Even more tantalizing, the lightest superpartner, often the neutralino, could be the elusive dark matter, silently weaving through galaxies, its gravity holding stars together without a shred of light. Picture trillions of these particles drifting like ghosts through your body right now. their collective mass shaping the universe while remaining utterly invisible. Yet SUSY has a problem. We haven't found it. The Large Hadron Collider, designed in part to hunt for superpartners, has come up empty. The simplest versions of the theory predicted particles light enough to detect by now, leading some to declare SUSY dead. But like a clever fugitive, supersymmetry might just be hiding in plain sight. Perhaps superpartners are heavier than expected, or they decay too quickly to spot. Maybe they're camouflaged by extra dimensions or hidden interactions. The math is too beautiful to abandon entirely. Many theorists argue we've only scratched the surface of SUSY possible forms. This leaves us with a thrilling question. If supersymmetry is real, could it be the key to gravity's quantum enigma? The graviton, gravity's hypothetical messenger, might have a superpartner to the gravitino, a particle that straddles the divide between force and matter. In some models, gravitinos could be dark matter themselves, or they might mediate gravity in ways we've yet to imagine. SUSY doesn't just offer new particles, it suggests a deeper harmony, a universe where forces and matter are two sides of the same coin. But if supersymmetry remains out of reach, where else can we turn? The answer might lie in an even grander symphony of physics, one where particles aren't just mirrored but are vibrating strings dancing through hidden dimensions. That's the promise of string theory, a framework where gravity's quantum woes might finally meet their match. String theory paints a breathtaking vision of reality, one where gravity isn't a force but the symphony of infinitesimal strings vibrating through 10 dimensions. Imagine plucking a guitar string and hearing not a note but the gravitational pull between two planets. In this framework, every particle, from photons to quarks, is a tiny loop or segment of string, each vibration pattern corresponding to a different particle or force. Gravity's messenger, the graviton, would be a specific harmonic, a gentle hum in the cosmic orchestra. But here's the twist: these strings don't dance in the 3 dimensions we know. They're confined to a universe with 6 extra dimensions, curled up so tightly they're invisible, like the grooves on a vinyl record too fine for the naked eye to see. This compactification could explain gravity's baffling weakness. While electromagnetism and nuclear forces play out in our familiar 3-dimensional stage, gravity's strings might vibrate across all 10 dimensions, diluting their influence in our observable world like a whisper lost in a cavern. It's as if gravity is trying to shout through a wall of pillows. The extra dimensions muffle its strength, leaving only a faint echo in our reality. This elegant sleight of hand wouldn't just reconcile gravity with quantum mechanics. It would weave all fundamental forces into a single, unified tapestry. Enter M-theory, string theory's most ambitious descendant. By adding an 11th dimension, it stitches together 5 competing string theories into one grand framework, suggesting our universe might be a membrane, or brain, floating in a higher dimensional space. In this scenario, gravity could leak between brains, explaining why it feels so feeble compared to other forces. The math is undeniably beautiful, a labyrinth of equations where symmetry and geometry reign supreme. But beauty alone isn't proof. Decades after its birth, string theory still hasn't produced a single testable prediction. Without experimental validation, it risks becoming a cathedral of pure thought, stunning but untethered from reality. Yet physicists cling to it for good reason. String theory's mathematical consistency is unmatched, offering plausible solutions to black hole entropy and quantum gravity where other theories stumble. It's the only framework that naturally includes gravitons, weaving them into the quantum fabric without force. And then there's the tantalizing possibility that hidden dimensions might one day reveal themselves, perhaps in particle colliders, where microscopic black holes could flicker into existence, or in subtle gravitational anomalies that betray the universe's true shape. So is gravity the music of hidden dimensions. The idea is poetic, but the score remains unfinished. For all its elegance, string theory's silence in the lab has led some to explore a radically different path, loop quantum gravity, where spacetime isn't a smooth continuum but a network of interwoven threads, each carrying a quantum of area or volume. No extra dimensions, no vibrating strings, just a universe built from the ground up, one loop at a time. While string theory weaves gravity into a symphony of hidden dimensions, loop quantum gravity takes a radically different approach. It dismantles spacetime itself into a vast cosmic network of interwoven threads. Picture the universe not as a smooth, continuous fabric, but as a tapestry of tiny, indivisible loops, each carrying a quantum of area or volume. These loops knot together to form the geometry of space, creating a granular structure so fine that even the tiniest distances are built from these fundamental atoms of spacetime. It's like zooming in on a digital photo until you see the individual pixels, except here, the pixels are the very building blocks of reality. This granularity solves one of gravity's thorniest problems, singularities. In Einstein's Relativity, black holes crush matter into infinitely dense points where physics breaks down. But in loop quantum gravity, spacetime's discrete structure prevents total collapse, like a mesh too tight to rip. Instead of a singularity, a black hole's heart becomes a seething quantum region where spacetime loops twist and knot, creating a bounce that could even birth new universes. The math behind this is breathtaking, predicting black hole entropy with startling accuracy, tying the number of microscopic loops to the area of the event horizon, much like counting the atoms in a crystal. Yet loop quantum gravity faces its own hurdles. While it elegantly blends gravity with quantum mechanics on tiny scales, stitching it into cosmology, the study of the universe as a whole has proven messy. The theory struggles to explain cosmic inflation or dark energy, leaving gaps where string theory flexes its muscles. Some physicists argue that without a clear path to experimental proof, loop quantum gravity risks becoming a beautiful abstraction, a theory more comfortable with equations than telescopes. But what if the answer lies in merging these two perspectives, combining loops with geometry in a way that's both discrete and dynamic? Enter causal dynamical triangulations, a framework that rebuilds spacetime from the ground up using tiny, triangular chunks of geometry. Imagine assembling the universe like a cosmic Lego set, where each piece connects only in ways that respect causality. No time travel, no paradoxes, just a self-consistent cosmic lattice. Simulations of this model show something astonishing. At large scales, the jagged quantum structure smooths out, effortlessly reproducing the four-dimensional spacetime we know. It's as if the universe knows how to hide its quantum stitches when we're not looking too closely. The question remains, is spacetime a shimmering mesh, a vibrating string, or something else entirely? The beauty of these competing theories isn't just in their answers, it's in how they force us to rethink the very nature of reality. Whether loops or strings win the day, one thing's certain: gravity's final theory will rewrite not just physics, but our place in the cosmos. Imagine folding a piece of paper into intricate origami, each crisp crease transforming a flat sheet into a three-dimensional shape. Now picture spacetime itself undergoing a similar transformation, not with paper, but with tiny triangular building blocks that snap together to create the fabric of reality. This is the essence of causal dynamical triangulations, a bold approach to quantum gravity where the universe emerges from the simplest possible geometric rules. At its core, the theory treats spacetime as a mosaic of microscopic triangles. or more precisely, four-dimensional analogues called simplices that connect only in ways preserving causality. No time loops, no paradoxes, just a cosmic jigsaw puzzle where every piece locks into place with strict cause and effect precision. What's astonishing is how such basic ingredients can spontaneously generate the universe we recognize. When researchers simulate these triangulations at large scales, something remarkable happens. The chaotic jumble of geometric chunks smooths out, giving rise to the four-dimensional spacetime of general relativity. It's as if the universe knows how to hide its quantum scaffolding when we step back, much like a pointillist painting resolves into a coherent image from a distance. This effortless transition from quantum granularity to classical smoothness is one of the theory's crowning achievements, offering a rare bridge between the tiny world of quantum physics and the vast cosmos of relativity. Yet for all its elegance, causal dynamical triangulations face a glaring challenge: experimental validation. Unlike string theory's extra dimensions or loop quantum gravity's granular spacetime, this approach offers few clear signatures for astronomers or particle physicists to hunt. The triangles themselves are unimaginably small, far beyond the reach of any conceivable microscope, leaving the theory in a precarious position, mathematically compelling but hanging in a vacuum of proof. Some argue this isn't a flaw but a reflection of how deeply hidden quantum gravity's secrets might be. After all, if spacetime's true structure only reveals itself at scales a trillion times smaller than an atom, absence of evidence isn't surprising, it's inevitable. This raises a profound question. Is the universe fundamentally a puzzle waiting to be assembled, its laws encoded in geometric rules we've yet to fully decipher? The answer might lie in an even stranger idea: asymptotic safety, where gravity's quantum fluctuations could magically cancel each other out at ultra-high energies, rendering the theory safe from the infinities that plague other approaches. Like a cosmic self-correction mechanism, asymptotic safety suggests gravity might tame itself, no extra dimensions or hidden layers required. But that's a story for another fold in spacetime's ever-unfolding origami. What if gravity, the force that sculpts galaxies and bends the fabric of spacetime, possesses a hidden ability to heal itself, like a river smoothing its own rough edges over time? This is the tantalizing promise of asymptotic safety, a daring idea where gravity's quantum chaos might cancel itself out at unimaginably high energies, sparing the theory from the mathematical meltdowns that plague other approaches. Picture a tightrope walker who wobbles violently at first but finds perfect balance the faster they move. Gravity, in this view, could stabilize itself as energies approach cosmic extremes, like those in black holes or the seething infancy of the Big Bang. Renormalization, the process that tames infinities in quantum field theory, has long been gravity's Achilles heel. While electromagnetism and nuclear forces submit to this mathematical cleanup, gravity's equations explode into nonsense when quantum corrections pile up. Asymptotic safety proposes a loophole. What if gravity's quantum fluctuations aren't unruly weeds but precisely tuned gears, interlocking in a way that keeps the theory finite and predictable? Black holes become the ultimate testing ground. Near their singularities, where densities and energies skyrocket, asymptotic safety suggests gravity's self-correcting nature might prevent the equations from blowing up, replacing infinite collapse with a quantum bounce or a smooth, ultra-dense core. The early universe offers another clue. In its first fleeting moments, temperatures and energies were so extreme that particles behaved like waves in a boiling ocean. If gravity is asymptotically safe, this primordial frenzy wouldn't tear spacetime apart but instead trigger a self-regulating equilibrium, like a thermostat kicking in to prevent overheating. Some models even suggest this could explain inflation's explosive expansion without invoking ad hoc fields, gravity's own quantum resilience powering the universe's rapid growth. Yet for all its elegance, asymptotic safety remains a work in progress. The theory lacks a complete mathematical framework, relying on approximations that critics argue might mask deeper inconsistencies. Without experimental signatures like subtle imprints in the cosmic microwave background or deviations in gravitational waves, it risks becoming a beautiful hypothesis untethered from reality. Supporters counter that absence of disproof isn't proof of absence. After all, atoms were once just a handy abstraction until we glimpsed them directly. This uncertainty nudges us toward an even stranger possibility. What if spacetime's smoothness is an illusion, and its true geometry is built from something beyond mere points and lines? Enter non-commutative geometry, where coordinates no longer obey the tidy rules of multiplication we learned in school. Here, the very concept of here and there blurs, suggesting that at microscopic scales, spacetime might be more like a tangled quantum web than a crisp grid, a structure where gravity's self-healing properties could arise naturally from the fabric's inherent fuzziness. What if the smooth, predictable coordinates of space and time we take for granted are nothing more than an illusion, a convenient fiction that crumbles when we peer too closely? This is the radical proposition of non-commutative geometry, where the very idea of here and there becomes blurry, like trying to pinpoint the exact edge of a cloud. In this strange realm, spacetime coordinates no longer obey the tidy rules of multiplication we learned in school. Instead, measuring position in one direction affects measurements in another, creating a fundamental fuzziness at the smallest scales. It's as if the universe has a built-in uncertainty principle for space itself, not just particles, a cosmic hesitation that prevents spacetime from ever being perfectly sharp. This granularity could solve some of gravity's most vexing problems. Take black hole singularities, those infinitely dense points where Einstein's equations break down. In non-commutative geometry, spacetime's inherent fuzziness acts like a safety net, preventing matter from collapsing into a true singularity. Picture a black hole's core not as a mathematical nightmare, but as a swirling, quantum froth where coordinates blur and overlap like ink dissolving in water. Even the Big Bang might lose its explosive edge, smoothed into a gentle quantum bounce by the universe's refusal to let anything, even spacetime, be infinitely small. The math behind this is both elegant and bewildering. Instead of ordinary multiplication, physicists use something called a star product, where coordinates interact in twisted, unpredictable ways. These equations suggest that at scales a billion trillion times smaller than an atom, spacetime might resemble a tangled network of relationships rather than a static grid. It's as if the universe's blueprint were written in a language where words change meaning depending on the order you read them, a cosmic game of quantum Scrabble where the rules shift with every move. Yet for all its theoretical promise, non-commutative geometry remains silent in the lab. No experiment has detected spacetime's fuzziness directly, leaving the idea suspended between inspiration and speculation. Critics argue that without empirical hooks, the theory risks becoming a beautiful abstraction, a mathematical daydream with no anchor in reality. Supporters counter that absence of evidence isn't evidence of absence. After all, quantum mechanics once seemed just as esoteric before technology caught up with theory. This raises a dizzying question. If spacetime isn't smooth and continuous, what is it really made of? Could its apparent solidity emerge from something even stranger, a deeper layer of reality where concepts like here and now don't exist at all? The answer might lie in the next frontier of physics, where spacetime itself isn't fundamental but arises from the chaotic hum of quantum information. And that's where the story takes its most unexpected turn. Spacetime as we know it, smooth, continuous, and infinitely divisible, might be nothing more than a grand illusion, a cosmic magic trick emerging from a deeper, weirder reality. Imagine the universe not as a stage where particles and forces perform, but as a vast, humming network of quantum entanglement, where every connection between particles subtly weaves the fabric of space and time itself. This is the startling premise of emergent spacetime, where gravity isn't a fundamental force but a side effect of quantum relationships, like the way traffic patterns emerge from countless individual drivers, none of whom intend to create a gridlock. At the heart of this idea lies tensor networks, mathematical frameworks that describe how quantum systems entangle across vast distances. Picture a cosmic spiderweb, where each strand represents a quantum link between particles, and the tension across the web creates the illusion of geometry. The more entangled two particles are, the closer they appear in spacetime, even if they're light years apart. This isn't just metaphor. The AD/CFT correspondence, a breakthrough in theoretical physics, suggests that a lower-dimensional quantum system without gravity can perfectly encode a higher-dimensional universe where gravity exists like a hologram projecting a 3D world from 2D data. In this view, spacetime doesn't underpin reality, it crystallizes from it. The implications for gravity are profound. Instead of mass-warping spacetime, as Einstein taught us, entangled quantum states could generate spacetime's curvature from the bottom up. Think of it like a trampoline sagging under weight, except the trampoline is stitched together by the collective interactions of trillions of quantum threads, and the weight is just the density of their entanglement. Black holes, those ultimate spacetime warps, might be knots of maximal entanglement, their event horizons marking the boundary where quantum connections become so dense they bend reality into a closed loop. Even dark energy could be reinterpreted as the universe's entanglement gradually diluting as space expands, like a web stretched too thin to hold its shape. Yet for all its elegance, emergent spacetime remains speculative. No experiment has yet captured spacetime forming from entanglement, and the math is so abstract it's often called the physics of the possible. Critics argue that without empirical hooks, the theory risks being a beautiful mirage, a story we tell to make sense of math that's outrun our intuition. But supporters counter that every revolution in physics began as a heresy. Once, atoms were just a philosophical guess, now we photograph them. This raises a dizzying question. If spacetime is a quantum graph, who or what is drawing the lines? Enter observer-driven gravity, the idea that reality might not just be written in quantum code, but that the act of observation itself could shape the rules. After all, in quantum mechanics, particles don't settle into definite states until measured. Could spacetime and the gravity it carries be just as malleable, a cosmic canvas waiting for a brushstroke from consciousness? What if gravity, the force that shapes galaxies and pins us to the Earth, isn't just out there in the universe, but shaped by our very perception of it? This is the wild frontier of observer-driven gravity, where the act of measurement might not just reveal reality but actively mold it. In the quantum world, particles famously exist in blurred superpositions until observed, collapsing into definite states under the gaze of a conscious observer. Some theorists like John von Neumann and Eugene Wigner took this further, suggesting consciousness itself plays a role in stitching together reality. Apply that to gravity and the implications are staggering. Could spacetime's curvature depend not just on mass and energy, but on the presence of observers? The math behind this is speculative but tantalizing. If consciousness, or even just quantum measurement, influences gravity's behavior, it might explain oddities like dark energy's acceleration. Picture the universe as a vast quantum system. As observers proliferate, their collective measurements could subtly tweak spacetime's geometry, like invisible hands pressing on cosmic clay. This isn't mainstream physics. Most scientists dismiss it as philosophy dressed in equations, but the questions it raises are irresistible. Does the cosmos need witnesses to give it form? Or is this just a modern echo of the old thought experiment? If a tree falls in an empty forest, does it make a sound? Now shift the lens to holographic dark energy, a more grounded but equally mind-bending idea. If the universe is a hologram, as some theories suggest, then dark energy might not be a mysterious force but a side effect of information encoded on the cosmic boundary. Imagine the universe's expansion as a projector adjusting its focus. The further it stretches, the more the image distorts, creating the illusion of repulsive energy. Here, gravity's weakness at cosmic scales isn't a flaw but a clue. It's diluted because it's leaking into the higher dimensional bulk of reality, like ink seeping through paper. The thread connecting these ideas, reality, might be far more malleable than we thought. Whether through conscious observation or holographic codes, gravity could be less a fixed law and more a dynamic dialogue, a conversation between the universe and those who try to understand it. And if that's true, the next great leap in physics might not come from a telescope or a particle collider, but from rethinking who or what holds the pen that writes the cosmic rules. What if dark energy, the mysterious force accelerating the universe's expansion, isn't a force at all, but a cosmic side effect of the universe hitting its information limit? This is the spine-tingling premise of holographic dark energy, an idea that ties the fate of the cosmos to the holographic principle's radical claim. The universe might be a projection of information stored on its outer boundary. Imagine a computer running a simulation. As the program grows more complex, it demands more memory. Now picture the universe as that program, its accelerating expansion not driven by some exotic substance, but by the sheer need to keep up with the information it contains. Every new galaxy, every particle, every quantum flicker adds to the cosmic ledger, and at some point, the system must expand to free up space, like a hard drive defragmenting itself to avoid crashing. The math behind this is as elegant as it is strange. In holographic dark energy models, the universe's information content scales with its surface area, not its volume, a direct nod to the holographic principle. As space grows, so does the boundary where information is encoded, but there's a catch. The rate of expansion must accelerate to balance the books. This creates a feedback loop where more space means more boundary, which in turn requires even more space, leading to the runaway acceleration we observe. It's a cosmic catch-22, where the universe's own information demands push it to expand faster, not because of dark energy's repulsive push, but because the cosmos is literally making room for itself. Compare this to the cosmological constant, Einstein's infamous biggest blunder turned accidental prophecy. In that model, dark energy is a fixed energy density woven into spacetime itself, a static backdrop against which the universe plays out. Holographic dark energy, by contrast, is dynamic, its strength evolving with the universe's size. Observations of supernova and galaxy clusters can't yet definitively choose between the two, but holographic models have a tantalizing edge. They naturally avoid the "why now?" problem. The cosmological constant's value is absurdly fine-tuned. Why is dark energy's kick so weak compared to quantum predictions, yet just strong enough to dominate the universe at this exact moment in cosmic history? Holographic dark energy sidesteps the issue by linking acceleration to the universe's age and size, making today's expansion rate less a coincidence and more an inevitable phase in an information-driven life cycle. Yet for all its explanatory power, holographic dark energy shares a flaw with its rivals. It's still ad hoc. The theory doesn't yet derive from first principles, leaving its connection to quantum gravity as more of a suggestive hint than a rigorous proof. It's as if we've found a key that fits the lock, but we're not entirely sure if it's the right door. This uncertainty opens a dizzying possibility. Could the universe be a kind of self-updating algorithm, rewriting its own rules as it expands? A cosmic program where spacetime isn't the stage but the output, continuously generated by some deeper computation. That line of thinking leads straight to vacuum metamorphosis, an even wilder idea where dark energy isn't just information-driven, but a phase transition in the quantum vacuum itself. Picture water freezing into ice. At a critical point, the system flips into a new state with entirely different properties. If the universe underwent such a shift, the vacuum of space might have reconfigured itself, switching on dark energy's acceleration like a cosmic thermostat clicking into place. The implications are staggering. If true, we're living in the aftermath of a quantum upheaval, riding the wave of a space-time-altering event that's still unfolding. And if that's the case, gravity's story is far from over. It's just entering its most surprising chapter. Vacuum metamorphosis is one of the boldest ideas in modern cosmology, a theory suggesting dark energy isn't some mysterious substance, but the cosmic equivalent of water freezing into ice. Picture the universe's vacuum, that seemingly empty space between stars, undergoing a sudden phase transition, flipping into a new state with entirely different gravitational properties. It's as if the universe hit a hidden switch, activating dark energy's repulsive push, not by adding something exotic, but by rearranging the quantum foundations of reality itself. This idea borrows from the Higgs mechanism, where particles gain mass by interacting with an invisible field that permeates the cosmos. Just as the Higgs field froze into its current state shortly after the Big Bang, giving rise to the masses of particles we know today, vacuum metamorphosis proposes that gravity itself might have undergone a similar cosmic chill, a phase change that altered its behavior on the largest scales. The math behind this is compelling. By treating dark energy as a thermodynamic phase transition, theorists can reproduce the universe's accelerating expansion without fine-tuning arbitrary constants. Instead of inventing a new form of energy, they're tweaking the rules of an old one, letting gravity's own evolution do the heavy lifting. The predictive successes are hard to ignore. Vacuum metamorphosis naturally explains why dark energy's effects became dominant relatively recently in cosmic history, around 5 billion years ago. If the vacuum transition occurred as the universe cooled past a critical threshold, it would mirror how water abruptly turns to ice at 0 degrees Celsius. Observations of supernova, galaxy clustering, and even the cosmic microwave background align eerily well with this timeline, as if the cosmos left breadcrumbs pointing to a gravitational phase change. Yet the theory isn't without gaps. The microphysics behind such a transition, what exactly triggers it, or what quantum fields are involved, remains murky. Is there a gravitational Higgs lurking in the vacuum, waiting to be discovered? Or is spacetime itself capable of collective phase shifts, like a material switching between conductor and insulator? These questions plunge us into the speculative deep end, where the line between established physics and inspired conjecture blurs. This uncertainty opens a provocative possibility. What if gravity's phase change wasn't uniform, Could pockets of the universe have frozen differently, creating domains where gravity behaves in exotic ways? It's a wild thought, but one that ties neatly into another radical framework, unimodular gravity, where the laws of physics simplify dramatically if we assume spacetime's volume is fixed. In this view, dark energy's acceleration isn't driven by a new field or phase transition, but by the universe's stubborn refusal to stretch its container. The implications are profound. Gravity's quirks might not be bugs in the equations, but features of a cosmos that's been playing by hidden rules all along. What if the universe isn't infinitely stretchy but more like a balloon with fixed volume? No matter how much you inflate it, the total amount of space stays constant. That's the mind-bending premise of unimodular gravity, a radical reimagining of Einstein's equations where spacetime's volume isn't just a background feature but a rigid constraint, like the frame of a canvas limiting how much paint can be spread. In this view, dark energy's mysterious push isn't caused by some exotic substance. It's the cosmic equivalent of a Lagrange multiplier, a mathematical tension that arises when the universe tries to expand beyond its predetermined capacity. Picture a crowded elevator. No matter how people shift, the total space stays the same, and the pressure builds until someone steps out. Now replace the elevator with spacetime, and the people with galaxies' dark energy might just be the universe's way of saying, no more room. The math behind this is startlingly elegant. By fixing spacetime's volume as a constraint, unimodular gravity sidesteps some of quantum gravity's thorniest problems, like the infamous cosmological constant problem. In standard theories, quantum fluctuations should flood the vacuum with absurdly high energy, making the universe tear itself apart. But unimodular gravity tames these infinities by treating them as mere shifts in reference, like recalibrating a scale to ignore static. The result, a theory where dark energy emerges naturally, not as an arbitrary add-on but as a consequence of spacetime's stubborn refusal to exceed its quota. It's as if the cosmos comes with a built-in volume knob and someone set it to max at the Big Bang. Yet unimodular gravity remains a niche idea, championed by a small but passionate group of theorists. Critics argue it's too restrictive. Why should spacetime's volume be fixed when everything else, from energy to entropy, is free to fluctuate? Others counter that the universe loves constraints. After all, light speed limit and quantum discreteness are non-negotiable rules that shape reality. Maybe volume is just another cosmic invariant, hidden in plain sight. This debate leads to an even stranger cousin, shape dynamics. If unimodular gravity locks spacetime's volume, shape dynamics goes further, suggesting that only the universe's shape matters, not its size. Imagine a rubber sheet that can bend, twist, and fold but never stretch or shrink. In this framework, gravity isn't about curvature, but about how configurations evolve relative to one another, like a cosmic game of musical chairs where the chairs can morph but never multiply. It's a radical democratization of physics where scale becomes irrelevant and only relationships rule. The implications are profound. If shape dynamics is right, the universe might not be expanding at all, just rearranging itself in ways that mimic growth, like a crumpled piece of paper smoothing out to fill a table. Dark energy's acceleration could then be an illusion, a byproduct of misreading shape changes as volumetric growth. It's a dizzying thought. What if the cosmos isn't getting bigger, just unfolding, whether through fixed volumes or evolving shapes? These theories force us to confront a deeper question. Is spacetime a dynamic actor or a passive stage? The answer might lie not in the equations but in the silent hum of gravitational waves, where subtle anomalies could betray the universe's true architecture. Until then, one thing's certain: gravity's rulebook is still being written, and the next page might rewrite everything. What if time, the steady tick of the universe's clock, isn't a fundamental feature of reality, but an illusion conjured up by gravity itself? This is the provocative heart of shape dynamics, Julian Barber's radical vision where the cosmos isn't a movie playing frame by frame, but a gallery of frozen moments, each a unique configuration of space. In this timeless physics, gravity doesn't bend space-time. It emerges from the relationships between these snapshots, like the flipbook illusion of motion springing to life from still images. Imagine holding a handful of photographs. One shows the moon near the horizon, another high in the sky. Flip through them fast enough and you see movement. But in shape dynamics, there's no flipbook, just the photos themselves, with gravity as the hidden rule that tells you which image comes next. Barber's framework strips physics down to its barest essentials, pure geometry. Instead of tracking objects moving through time, shape dynamics focuses solely on how spatial arrangements relate to one another. The moon isn't orbiting Earth over minutes and hours. It's simply that one shape of the universe, moon here, naturally leads to another moon there, with no need for a clock to govern the transition. This mirrors relational quantum mechanics, where particles don't have absolute positions, only positions relative to each other. In both views, reality isn't a stage with actors and a script. It's a web of connections, with gravity and quantum mechanics as the invisible threads tying it all together. The implications for time are staggering. If shape dynamics is right, time isn't a river flowing inexorably forward, but a shadow cast by the changing geometry of the universe. Think of a sundial. The moving sun creates the illusion of time's passage, but it's really just light and angles. Similarly, what we perceive as time might be gravity's way of stitching spatial configurations into a coherent sequence. This turns Einstein's relativity on its head. Instead of spacetime as a unified fabric, space takes center stage, and time becomes a derivative, a cosmic afterthought. Critics argue this is a step too far. How do you explain entropy's arrow? The fact that eggs scramble but never unscramble without time's flow. Barber counters that entropy isn't about time, but about counting shapes. There are simply more disordered configurations for the universe to take, so it naturally tends toward them. It's not that time moves toward chaos. It's that chaos is statistically inevitable, like shuffling a deck into randomness. But the most tantalizing question remains. If time is gravity's shadow, what casts the light? The answer might lie in superspace, an even more abstract realm where every possible configuration of the universe coexists at once, a static landscape of every now that could ever be. Here, gravity isn't a force but a path through the wilderness of shapes, guiding the universe from one state to another without a single ticking clock. It's a vision so bold it redefines not just physics, but our place in the cosmos, a universe where time isn't the stage, but the play itself. Superspace isn't a distant galaxy or some sci-fi battlefield. It's the hidden arena where gravity's deepest secrets play out, a mathematical realm where every possible configuration of the universe exists at once. Picture a cosmic library filled not with books but with snapshots. One shelf holds a universe where Earth never formed, another where black holes dance in perfect spirals, and another where time runs backward. This is the stage for quantum gravity, where the wave function of the entire universe evolves not through time, but across an abstract landscape of geometries. Here, gravity isn't a force but a probability cloud, a shimmering haze of potential realities waiting to crystallize into the one we experience. At the heart of this idea lies the Wheeler-DeWitt equation, a daring attempt to merge quantum mechanics with general relativity. Unlike Schrödinger's equation, which tracks particles evolving through time, Wheeler-DeWitt eliminates time entirely, a feature so baffling physicists call it the problem of time. The equation describes a static universe, frozen in an eternal now, where change is just an illusion born from comparing one cosmic snapshot to another. It's as if the universe is a jukebox stacked with every possible record, and reality is the needle hovering between tracks, never quite landing. Critics argue this timelessness clashes with everything we observe, from aging stars to decaying atoms. Supporters counter that time might be emergent, like temperature arising from atomic chaos, a mirage that only makes sense when you zoom out. The real magic of superspace is how it reshapes our view of reality. In quantum mechanics, particles exist in superpositions both here and there, spinning up and down until measured. Superspace extends this to the cosmos. The universe itself could be in a superposition of shapes, a cosmic Schrödinger's cat where every possible curvature, every arrangement of matter coexists until something chooses one. But what does the choosing decoherence? Observers, the equations don't say, leaving us to wonder. Is our universe just the most probable branch in an infinite tree of geometries, or is there a deeper mechanism pruning the possibilities? This uncertainty nudges us toward twistor theory, a radical alternative where spacetime isn't the foundation but a secondary effect. If superspace is a library, twistors are its index cards, abstract mathematical objects that encode spacetime's structure in a way that makes quantum gravity almost intuitive. Instead of wrestling with curved geometries, twistor theory paints the universe as a web of light rays and interactions, where particles are knots in the fabric and gravity is the tension between them. It's a vision so elegant it makes you wonder, could the key to quantum gravity lie not in the equations of spacetime, but in the poetry of light? Twistor theory turns gravity's greatest mystery inside out. What if spacetime isn't the foundation of reality, but a secondary effect woven from something far more primal, light itself? Roger Penrose's visionary framework imagines the universe not as a stage of points and distances, but as a shimmering web of twistors, abstract mathematical objects that represent light rays at their most fundamental. Picture a beam of sunlight slicing through space. In our everyday view, it travels through spacetime, but in twistor theory, that light ray is spacetime, or at least the thread from which spacetime is spun. Every twist and turn of these twistor threads encodes the geometry we perceive as gravity, like a cosmic loom weaving the fabric of reality from strands of pure light. The elegance of this approach lies in its simplicity. Einstein's relativity treats spacetime as a dynamic, curving landscape, a rubber sheet warped by mass and energy. Twistor theory sidesteps this complexity by recasting gravity in terms of symmetries, the invisible harmonies that govern how light rays intersect and interact. Imagine two flashlights crossing in a dark room. In ordinary physics, their beams pass through each other unnoticed. But in twistor space, that intersection becomes a cosmic event, a knot of geometry where spacetime's structure is born. This reframing solves thorny problems almost effortlessly. Black hole singularities, for instance, dissolve into smooth twistor configurations, as if the universe's most violent phenomena were just tangled threads waiting to be combed straight. Yet for all its beauty, twistor theory has struggled to bridge the quantum divide. Quantizing twistors translating their ethereal geometry into the gritty language of particles and probabilities has proven as slippery as trying to catch light in a net. The equations resist, leaving tantalizing hints of a deeper unity but no clear path to a full quantum gravity theory. It's as if we've been handed a key to a door we can't quite locate, a puzzle wrapped in luminous mystery. This isn't just abstract math. twistors might hold the key to understanding why gravity is so weak compared to other forces. If spacetime emerges from light-like structures, its feebleness could be a side effect of being stretched thin across the cosmic loom, like a tapestry whose threads fray at the smallest scales. Some models even suggest that particles like electrons could be twists in the twistor fabric, their mass and spin arising from how these threads knot and curl. But if twistors are too ephemeral to pin down, perhaps gravity's secret lies in a different kind of weaving. Enter group field theory, where spacetime isn't built from light rays but from discrete chunks of quantum geometry, like pixels assembling into a hologram. Here, the universe isn't a smooth continuum but a vibrant network of interactions, each node a tiny quantum event echoing through the cosmic web. The shift is profound, from Penrose's luminous threads to a universe humming with algebraic relationships, where gravity emerges not from light alone, but from the collective hum of countless quantum conversations. Group field theory takes the wild idea of quantum foam, the notion that spacetime bubbles and churns at microscopic scales, and gives it a rigorous mathematical backbone. Imagine the universe not as a smooth, continuous fabric, but as a frothy network of abstract interactions, where every bubble is a tiny quantum event tied to the symmetries of group theory. These aren't physical particles or even points in space, but fundamental building blocks defined purely by their algebraic relationships. It's as if the cosmos runs on a hidden code, where the rules of geometry emerge from the way these abstract elements combine and interact, like a cosmic game of Tetris played with mathematical tiles. This framework shares DNA with loop quantum gravity spin networks, those intricate webs of quantized spacetime, but with a crucial twist. Where spin networks focus on discrete chunks of area and volume, group field theory zooms in on the process of creation itself. Think of it like the difference between studying a finished mosaic and watching the artist place each tile. Here, spacetime isn't a static structure but a dynamic foam, constantly reconfigured by the interactions of these group theoretic tiles. The equations describe how these elements collide, merge, and dissolve, weaving the fabric of reality moment by moment. It's a universe under construction with no foreman, just the probabilistic hum of quantum combinatorics deciding what forms next. The implications are dizzying. If group field theory is right, the Big Bang might not have been a single explosive event, but a phase transition in this quantum foam, a moment when the dice of creation rolled a certain way and our particular spacetime configuration crystallized. Other rolls could have led to entirely different universes, with alternate dimensions or even stranger physics. This isn't just multiverse speculation. It's a concrete mathematical possibility arising from the theory's equations. Yet for all its promise, group field theory remains in its infancy. The math is fiendishly complex, and while it elegantly reproduces features of general relativity and quantum mechanics in simplified models, scaling it up to describe our full, messy cosmos is like trying to chart a hurricane with a pocket calculator. Critics argue that without experimental predictions or observational hooks, the theory risks floating in abstract limbo. But supporters counter that every revolutionary idea starts as untestable speculation. Black holes and gravitational waves were once pure theory too. What makes group field theory tantalizing is its sheer audacity. It doesn't just tweak gravity's rules or add hidden dimensions. It suggests that space-time, matter, even causality might all be secondary effects, emergent patterns in a deeper, more vibrant quantum game. And if that's true, the ultimate question isn't just how gravity works, it's whether the universe is less a grand design and more a cosmic roll of the dice. From twisted space-time geometries to cosmic holograms, the sheer diversity of gravity's challenges is nothing short of breathtaking. We've journeyed through theories where gravity leaks into hidden dimensions, emerges from quantum entanglement, or even flickers in strength like a cosmic dial. Some frameworks treat it as an illusion, a side effect of information processing on the universe's edge, while others imagine it as a force with mass, its gravitons lumbering where photons zip. Yet for all their creativity, none have yet toppled Einstein's relativity from its throne. But here's the twist: that's not a failure of imagination. It's a testament to how radically our understanding could shift. The very fact that so many viable alternatives exist, each with its own compelling math and philosophical allure, proves gravity's reign isn't set in stone. It's more like a placeholder waiting for the next paradigm to rewrite the rules. The coming decade could be the turning point. Projects like LISA, the Laser Interferometer Space Antenna, will hunt for gravitational waves from supermassive black holes, potentially spotting anomalies that betray extra dimensions or modified gravity. Quantum gravity probes, from tabletop experiments with ultra-cold atoms to observations of primordial black holes, might catch spacetime's granularity in action. Even dark matter detectors, should they continue coming up empty, could force us to reconsider whether we've been chasing ghosts while gravity's true nature hid in plain sight. The universe has a habit of humbling our assumptions. Just ask Newton, who never dreamed his apple's pull would one day bend starlight. So where does that leave us? At the edge of a cosmic cliff, peering into the unknown, the wildest ideas, spacetime as emergent code, gravity as thermodynamic tax, aren't just sci-fi musings. They're serious science backed by equations as elegant as they are audacious. That's the thrill of physics. Today's heresy could be tomorrow's textbook. Which of these theories resonates with you? Do you see gravity as a cosmic mirage, a hologram's shadow, or something stranger still? Drop your thoughts in the comments. We're all part of this grand conversation. And if you're hungry for more mind-bending journeys through the cosmos, hit subscribe. The next breakthrough could drop at any moment, and you won't want to miss it. After all, history shows the universe loves a good